Is this visible?
Yes,
Yes,
sir.
sir.
Okay, let's start. Whatever we've discussed so far about we can say instruction set architecture, ISA, whatever so discussed. So now we are coming go very close to the you can say example, or you can say most suitable architecture of ISA, which is generally used inbuilt in time first, which was most suitably used. So instruction set architecture, we already understood that different computers have different instruction set. There is a very important point you must remember, that does not one ISA which is completely specific the Intel operating system cannot be applicable for Mac system or maybe MIPS or any other uh, system. Early computers had very simple instruction set, simplified implementation was there. Many modern computers also have simple instruction set. So actually this is the already we have discussed so far. So now we are going for a MIPS one example we have considered for a particular architecture. And the Mars simulator, whatever I have go already mentioned about the simulator which follow the MIPS architecture. One simulator which is built up should follow the one principle, and that is the MIPS architecture is followed. It used as example throughout the books. You just remember this point. In our books also, that means I told that we are following these books. I think you know computer organization architecture, the Hensey Davis Patterson. So in entire book, they follow this architecture. Okay. Now, though Stanford recently MIPS is commercialized by MIPS technology because they MediaTek, MediaTek one semiconductor industry are partnered with the Stanford, and now they are commercializing the MIPS architecture. So if you go, I think my browser is visible to you. Browser. Now
No,
you
sir.
see, if you click MIPS, automatically you now find the MIPS.com, because earlier it was open source. Now MIPS architecture, you try to get more exploration of the architecture. Actually there are now a number of cores, what are the classic core, what is the actually MIPS architecture, now how it is MIPS is following. So this is the open source architecture initial was there. Now Stanford is commercialized with some modification and more advancement. Now also that it happen that like patent live application, the patent they have done. Now you take and made accordingly yourself architecture you can design, and new system can be built upon on it. So that is the advantage of the MIPS. So now what happened that large share of embedded core market and typical many modern ISAs are simply mis reference are using. Now we will gradually go what happened in the mix. Suppose in the MIPS, arithmetic and subtract three operands. Now three operand means I am following what? Three address format. Am I clear? So suppose add ABC instruction you are writing. That means A is the source and B plus, sorry, A is the destination and B is the source, and A result should be stored into the A. So this type of instruction, three operands are used. So it is a three address mode. All arithmetic operations have this type of form. Design principle simply favors regularity. So what is the design principle criteria during the choosing of the MIPS? As remember, the design principle what I am there, simplicity. So very important point that your instruction should be very simple to understand. That makes a higher performance and lower cost. That is for simple instruction, though it is a little bit complicated because three memory operand they are using simultaneously. Now
Hello, sir.
suppose yes,
Sir, in the previous slide,
yes,
sir, add A, B, C and A gets B plus C. Both are equivalent.
which I am telling the meaning of the information. This is the meaning of the information.
Sir, not
This
getting the meaning, sir. Please, can you
meaning
please
that
repeat the?
means add A comma B comma C. It means that B and C will be added, then result will be stored on A. So A will get what? B plus C summation of the addition. That's I written here. A gets B plus C. That means summation of B and C will be stored on A. Is it clear?
Yes, sir. Okay, sir. Thank you.
Very simple question, no problem. But most welcome. First time you have started
No,
practice.
sir. No, sir. I have confused about at the location A, B plus C get stored. That I think.
Okay. No problem, no problem. Very good. But you asked question, I am very happy. Every time asked.
Okay.
Bogus for you, but very important for me. Don't worry. Okay. So
Yes, sir.
now,
Okay.
simplicity enables higher performance at lower cost. That is the part already I mentioned. Now you will find that C code. Suppose this is the code you have to implement. Now you need the result of this part and you need the result of the part, and then suppose this is X then Y. Then you can do the X minus Y. Am I correct or wrong? So to do this thing, how to do MIP? So MIPS first will do stored in a temporary register. Maybe you can consider here, this is the register. You just consider this is a register and these are the from another register or maybe memory. So I am considering as a memory location, and this must be either register or memory, but here you consider it from register bank. Okay, so temporary registers are like accumulator you can consider, or in accumulator also I can store if the T0 is used in the next exam, but it is not using here. So first initially in T0 G and plus H will be stored, so meaning of the instruction like in this way. Then T1 will take IJ, whatever I say, this is the T0, this is the T1. Okay, so I can say this is T0 and this is T1. I better I can write like in this way. So this is T0 and this is T1. Okay. Now after doing this thing, now you are getting this part. Here you will find that sub, that means T0 minus T1, then you will get the function and that will be stored the result in the F. So in the MIFS actually they are doing the computation part like in this way.
So I
Next
have
is
a question, sir.
yes.
So in the previous slide, we are using temp to store the results. Why can't
Yeah.
we use G and I, sir? We can save memory as well. I mean,
Yeah, I am telling that T0, if you use memory, the processor performance will be very slow because CPU most of the time CPU utilizes its own registers. That you just remember. Only for the store instruction, when you write store, that means save. You know, normal command is save. That time it will you use memory here. That means the content of T0 go and some location it will be stored in the memory. But always CPU do their execution most of the time with some CPU register. And to mention that CPU register, I am mentioning that it is as a temporary because the content will not be stored for infinite time here.
okay, sir.
Now next question is that MIF says 32 by 32 by register file. That is the very important. I already told just now that you told that why they are frequently using the registers, because for the accessing speed, and it is also the one of very example I will go for the directly the RISC architecture. So maybe reduced instruction set, less number instruction, but very fast and efficient set of instruction. So to understand, give the memory location, use dollar symbol or sometime you use in the hash. But in the MIF simulator, when you will operate in the Mars simulator, write the code, you have to use this sign. Okay. So first design principle, what is the first design principle? I mentioned is that simplicity, as simple as I can write the example. Okay, and this is the design issue when you design new
Sir, but
ISL.
prefix,
Yes,
sir, but the prefix for both temporary and saved variables are the same. It's dollar.
temporary variable and
Saved
save. No. Whenever that means any storing is happening, not in memory. That means in previous example, if we go for the previous example, I am not using any store or save option. I am telling that thing. I am not using this thing. If
okay.
you save and store, that time it is required memory operation. I am telling.
Okay, and that is the dollar for all variants of it.
Here means the dollar for the all the variable what are using, and mostly you can consider that is register based because has a huge frequently accessed data. Are you getting my point?
Okay, sir.
This is the verification list. So that's why 0 to 31 is number. 32-bit data called is a word. Here word mean in the MIPS. Word is the size is 32-bit in MIPS. Word size 30-bit. Then if is a the individual memory location, a location also 32-bit, and like in this way 32-bit registers are there. Getting the point? That's why it is called 32 by 32-bit register file. Very important. What is the MIPS actually have, and what you can use further using the MIPS. That both are very important. That's why I told in the processor they have mentioned 32-bit embedded microcontrollers, and you seen this visible? It is visible. This MIPS website is visible. Are you getting this website? 32-bit is visible to you? Okay. So that's why I'm telling you the size I already mentioned, that register file also 32-bit they are using. Now, second design principle, very important point. What is the second design principle? Smaller is faster. Just 1 minute. I have a got call. Okay. Sorry for the interruption. Now, in the design, is smaller is faster. That means always we try to do that add instead of multiple as less as possible you give, as less as possible. Don't give more than one instruction at a time. So it will become very critical for us. So our main target is that the main memory, that means millions of locations are there. So it does not mean that all the locations will be simultaneously will be accessed. So register utilization is the very important part. So the instruction set should use all the register properly, and if you go for the accessing the main memory part, as possible as less instruction you try to load and store. Now suppose in the whenever these instructions are there to implement using the MIPS architecture, so this is the syntax you have to follow. Initially I have to store this in S1 and S2, suppose, because first command will be LD, and LD you have to store S1 with the value G. Suppose some value will come G, that will be loaded in that like in this way. So after doing LD, that part I am not starting because it is a more the load store architecture in the register purpose. You know, when register architecture is there already I mentioned. So load store architecture is completely used. So in this case, loading part I am not mentioning, storing part also I am not showing. I am just showing the what happened in the instruction here. So it should be loaded first in the memory and then from memory to register, that we have done earlier so far. Now that's why written f to dot dot j, that means all these are in registers I have mentioned. Okay. Now S1 and S2 will be loaded, added to the temporary register T0. It may be S4, S6 or S7, anything. Then it should be again added and loaded to the memory, and then finally SG will be calculated. So this is the three address format MIPS are using. Second is that main memory used for composite data, that means for array, structure and dynamic, because in register one data at a time I am using, maybe 32-bit size or the word size. I can say one word per register, I can say I am using. So here main memory, but when composite data will be there, that means a data which is a collection of more than one. So that time I think this is a problem for the issue. So and structures also parts are there, and for dynamic data all these things require composite data, then only main memory is used instead of register. In the register individual data can be stored, the composite data cannot be stored. To apply arithmetic operation, load values from the memory into register, store result from register to memory. That's I told you what is the purpose of the store command. Okay, store, or also you can say from your mind, that is also called save. That result from register to memory, and from memory to register is loading purpose. Memory is byte address, that is the per word I told. Each address identifies 8-bit byte. Words are in memory, so address must be multiple of 4. Address must be multiple of 4 because see 8-bit byte, so 8 into 4, that is you will get the 32 byte bit address, and that will be the address for each of the locations. So this is the actually the syntax, or sorry, we can say the MIPS actually follow this standard. MIPS is big endian, so you can understand what does it mean big endian. Most significant byte will be in the list address of the word. So we are not using the list LF this one. So now C code, again here is the array is there. How array can be used in the MIPS? That means they are specifying the offset, and that will be the index. I think this is showing what mode? Index register mode. Am I correct? That is index register mode. Index 8 requires offset of 32. Offset 32, directly the memory location or base address will be stored. And G in sorry, in first example, G in dollar, H in S2, all these are register location, base address of A is in SC. So is the base register in the S register, so it is not the index register. I can say it is segment register, so base register mode is using. Okay, and now once this base register is loaded in term temporary register T0. So now T0 contain the, if it is a continuous memory location, the first base address on by T0, and that is calculated by the register plus offset. So that is called, I told this is base register. Is this point clear to you why it is called base register?
Sir, could you explain it again, sir? I'm a bit confused, sir.
I am telling that here, if you notice it properly first time, now I have to implement the array part. I have to index the array part. So first I have to know in the memory location where I have to start, and continuously I will access the location. Continuous I have to access the location. Then I have to first get this location part. To get this access, I have to estimate the effective address. Now effective address is there here, because this base address is first loaded in the register, that I have told base register, base address of A, that means for particularly array, is in $st. So register contain the base address. So it is base register. Getting my point? Now 32, that is the offset. It will be added. So initial location, then after second location will be after 32 bit. After that again 32 bit, because the offset value is like in this way it will go. Okay, then 32 bit is the enter value will present, next enter value 32, like in this way continuous will happen. So that's why I have mentioned here index 8 require offset of 32 and 4 byte per word. 4 byte per word, and each byte is 8 bit. Then what is the size? 8 4 the 32, so 32 bit. Is it clear? Per word size.
Yes, sir.
Okay. Now this is compile, first base address will be loaded to the T0. Then from the T0 start loading the S2. Okay. So add S1 which contain the value of I think it is S2. Sorry, S1 is the G, and H is the S2. So S2 will be added to the T0, the first value location, and come. Now you will get the first location of the base address, and corresponding all this will be added by sequentially. So that's I loading that. First will be done. Then again you go for the next location. So again you will go for storing this. This is the SW store word. Whatever addition you have done, you stored in the location of the memory. Then fetch the second one like in previous way and do the same calculation, and then again store the update. So like in this way, this load store architecture is used. See, load and store architecture in MIPS used. So
So why
how array is it?
48,
Yes.
sir? Store word, sir.
After calculating the first value, with the S2, H, and that value is already stored. And that is the, if you consider the segment and each byte is 4 byte, they mention what is the byte? In the previous slide, they mention 4 bytes per word. So one word contains 4 byte. So here is a 4 byte, here is a 4 byte, here is a 4 byte, here is a 4. That is 32. That's why this offset is value is 32, and that I have fixed here in the offset first. Okay. So offset of 32. It requires
Sir,
for indexing. Yes.
Why is it 48, sir? The next one, the store word part, sir. That's what I was asking, sir.
This.
Yes, sir. Yes, sir.
8
Okay.
because of 812.
Now, what is the difference between 32 and 48?
812, sir, storing
8 and 12.
yes, sir, 8 and 12.
4 bit.
Hmm?
4 into 12.
Sir,
4 into 12.
12 into 4 equals to 48.
See,
So
this is the offset. This is the offset I am telling. Offset it means your base address plus some address, you will got the location. Here also you know the base address, but you can't take this offset because that data is present there. You have to go that offset jumping from the base address to location 48 where it is present. Because after 32, you can use 4 byte, though 36 4 byte for each word. So 444, that means 32 plus 4, that means 36. 36 plus 4, that means 40. Okay. 40 plus 4, 44, and 44 plus 4, 4, 48. Are you getting my point? So like in this way, after this 4 location, next location 48 will be available. Is it clear?
sir, I have a question.
Yes.
Sir, in the stored word, instead of using dollar $S0, why are we using dollar $T0? Because we are storing that value into the memories instead of. So we should have used a saved variable instead of a temporary variable.
Now load store, load command doing like in this way. Store command load doing like in this way.
Oh,
Got it?
no, sir.
Load is from register to memory. So this is the direction is like in this way, and store command and load command memory to register like in this way. Syntax not same. This is
Okay,
the destination. This is the destination in case of store.
okay, sir.
Got it?
Yes.
Okay. So this happen here. Now point is that now see 32 is the offset, then 36, 30, 40, 44, 48. Now after 48 you will get the next byte addressable location where you have to store. That's why this offset is 48. Is it clear?
Yes, sir.
Maybe this is the base address, then 32 you are getting this one, base address plus 48 you are getting this one, because this is for continuous for this location. Okay. Next you go register versus memory. Register are faster. Already I have this for only for references I written. So you can study it because everything I mentioned. Now immediate operand. So some value directly will be operanded. So now earlier I have found register mode is your register direct and indirect both I have used. Now another mode I am using here, immediate addressing mode. Is it clear? Another mode is the immediate addressing mode. Is it clear? So now immediate addressing mode I have used here. So directly S3 and plus 4 will happen. The value of S3 will be added with 4 and that will be stored in the S3. See, I have written here add I. No subtract immediate instruction. That means just use negative of the constant. If you use no subtract instructions are there, so use add as a negative as a parameter. So it can be used. So the design principle too is very simple. If you use a plus b, you would like to get a minus b, a minus, you can write minus b like in this way. So this is the concept they are using here. Is it clear? Purpose is same. Now That means a adder can be used for addition as well as subtraction also. So they're used like in this way. Design principle number 3, make the common case first. Small constants are common. Immediate operands avoids the load instructions. So as possible as if you have some addition with some variable, you can go for the immediate addressing mode. Now there are also MIF register 0 is the constant 0 cannot be overwritten. So in register 0, this is a constant value, always 0 is present there. So it cannot be overwritten there.
Sir, could you, sir, what, I did not understand the design principle 3, sir. Could you explain that again, sir?
Which one?
Sir, design principle 3, sir.
Digit easy case, that means suppose I have to add 0 with some variable. Okay, so they are asking that the principle was that make the common cases first. If it is happen every time you have to use 0 or something else or some constant value initially, by default it happened that no value should be initialized. In C programming also coding guideline that no variable should be initialized. So every variable when you declare, you give by default value 0. So how will specify the 0 in the register cases? So a register is there, name I have given 0, which contains the value 0. So you can't overwrite it. Otherwise, what happen? Every time a register will be loaded with the 0 and then 0 will be added. That means $S1 and $S2 suppose, and S2 will be loaded with the 0. So to avoid this thing, I am directly define a register with value 0 and call the register only sufficient. So no load here happen. So some common cases, I can decrease the loading time. Are you getting my point or not? I can avoid it.
Yes, sir.
Loading time. Is it clear? So that's why some constant operation, it though this type of thing cannot be overwritten in this one. So this is specifically this used for to avoid the loading time. Maybe you have found that accumulator, whenever any value present in the accumulator, by default it should be stored in the location, maybe as 0 location or maybe as 1 location. So by default it will be stored there in parallel. There is another issue, it will be stored, but here it happened that the register is not loaded. It is by default loaded with this one and permanently will be always show 0, maybe shorted with the ground. So always get the value 0 there. So I have not to load, I do no need to load 0 there initially before adding something. So directly you call the register. So it decrease the or avoid the loading time. Is it clear? Third principle is clear.
Yes, sir.
Yes, sir.
Now the
Yes, sir.
range of a n bit number I have given, suppose 0 to 2 to the power n minus 1, that already I discussed in immediate upper range, how 32 bit numbers will happen. That all are unsigned. In case of unsigned number that I mentioned, the minus 1. Okay, in signed case this will be plus 1, I have to mention. So using 32 bit you can write, you can go up to, this is the location, up to the power 32 you can go. Okay, and finally minus 1 value, then you will get the one less value here. That's why see some odd number is there. Now the sign number, you just check the sign number range, minus 2 to the power n minus 1 to the power. In case of unsigned, you see that it start from 0 to this. But in case of unsigned number, it is start from minus, because it's a sign number. So sign number negative and both positive you have to consider. That's why up to minus 1. Peculiarly you follow this one. Most of the time your student get confused this part. So to the power n minus 1 in positive side. Here also one more side is there. You have to add this part also to it to get the range of the sign number. Unsigned always from 0 to 2 to the power n minus 1. You're getting this below to the n minus 1, but in case of sign I should be n minus 1 then minus 1. So that is the actually for sign and unsigned that I mentioned here. Now in twice complement sign, I think in digital logic we have studied so far. So 1 for negative and 0 for non-negative number, and this cannot be represented in our cases. So you know this already mentioned in our example that minus 2 to the power n minus 1 is the lowest range. Here that's why this is not possible from our side. Non-negative numbers have the same unsigned and twice complement representation. So I have given some specific example there. It is 0, but I have given here 1. So for your case it will be minus 0, but that is not accessible or not useful. So this is the specific two number you just mentioned. Here you can get it. And this is the maximum value you will get, and 0 is the most positive values. So we can write like in this way, that indicate the first below most significant bit, always 0 for positive and 1 for negative. So complement and add 1. I think twice complement you have studied.
Yes, sir.
Studied. So that's why I am going very fast one by show. Sign extension. In MIPS instruction said extend immediate value. LB and LH extend load byte and half word, and BEQ and BNA extend the displacement. Branch for equality condition and branch for not equality condition. So that is also for displacement possible. If some condition met, then branch, then go for another location. That means you'll get some displacement from the code, and also from not equal also you can get the same displacement using your condition. Unsigned values extend with only zeros part only. More than 0 it is possible, less not possible. And example that 8-bit to 16-bit conversion plus 2 and minus 2 that we have seen here. So you just check that plus 2 how I've written, and twice complement up to this you fix, and rest of the part you just complement it, and automatically by signing that you will understand that is the negative. The twice complement most suitable comparing others. Now instructions are encoded in binary called machine code. So that's the MIPS code we have used here. Now you can use register number T0 to T7 or register 8 to 15s are using this temporal registers. T8 to T9 are register for 24 to 25, and 16 to 32 particular registers are there. So like in this way you can renaming all these things and use it. MIPS register instruction format. So it is a very important for all of you. Just listen that in the MIPS, if the source register, it is the register for operand, and for it is the for destination, and you will not function all this. That means these are format, instruction format, register instruction format, how they are using, and this is the opcode. Because I think this all this part you just for reference I am giving. This is for reference. As soon as you study, after some time you will find that all these things I will discuss in the March simulator. OP means operation code. RS first source of instruction, that is the first source. Second, the register number is the second one. RD is the destination number. It does not mean that you have to write here, but generally we write in the MIPS as the RD first, then RS, RT like in this way. But here just I am telling that this is the format you have to use. So shift, you can give some bit and some function code if opcodes are extended. I will explain here. I will explain later. See, now this is the temporary register add. S and S2 will be added and that will be stored. You see how we have mentioned these values here. Okay, so this is for only for register purpose. Same, you can use the hexadecimal code, compact representation of the B string. Someone can ask base 16 is more compact than our binary. So actually another instruction format I have that means immediate instruction mode, that is constant, or you can say address also. This is the source, sorry, to instruction, and here also if I can say if these two are appended, I can do like in this also. So RT here mentioned is the destination or source register. It can be both, is possible. Immediate arithmetic and load store instruction. So first you have to load this and directly add this value and then store the register. So these are all what I think is very compact and cost. So the constant also using maybe direct value, some $1 or sorry 1 or 2 like in this way, or some register, specific register also, zero register like in this way can be used. Design principle 4, good design demands good compromises. That means you have to also compromise the hardware and all these things. Different formats complicate decoding but allow 30-bit instruction uniformly. So I know multiple length instruction will be very good for us. For multiple instruction set will compass saving the memory. But what happened that it will complicate the issue. Here we are using 32-bit instruction format unitly. Then a fixed length instruction. So there is another issue is the length of the instruction always fixed. They will not vary. Keep formats as similar as possible, and that's why I'm telling you in the MIFs the extended opcodes are not allowed. Is it clear why extended opcodes in the MIFs not allowed? Extended opcodes in the mix not allowed. Okay, so one stored program concepts I mentioned here. So that's is the picture. Normally the instruction they represented in the binary just like data. Instruction and data stored in the memory. That is the very important point. Program can operate on programs, that means compiler linkers like example, and binary compatibility allows compiled program to work on different computer. That is the instructions architecture purpose. So some logical operation like most of them are C-like operation. I think we have used, and shift right and shift left in Java and C, and whatever in the MIFS command for this one. Just you follow the MIFS command. Same, your operation you will implement with this one. Your operation implement with this one. LL RL. This is the ALL and this is the RL. Okay. Now shift operation also I have given multiple by 2, SRL by IBS and divided by 2i. So like in this way, all the examples gradually I have shown to show you that the how it is following in the useful example. So the slide will be given in the website. So sorry, in the Moodle I will not show the slide. This for our references I will give you maybe in WhatsApp because it is some copy issue, right issues there. So you can study, but publicly I can't show in the website. If you tell that our SAR is distributed, I will be in official problem because copyright issue will be there. Okay, so for you study you can use it. Okay, otherwise from the books also you can study. That is our Deputy Hennessy Patterson books. You will find this one. See the use of zero here. The register zero always read as zero. Can you tell me why it is used? Which principle it is following this? Principle, design principle?
Third,
Third.
Third,
Very
sir.
good. Yeah. So it's a convenient one.
make
Part
the
we can
common
use.
case
Yeah.
first.
So all the design principle you know that is required to implement any that means any instructions architecture. This is the use case. Actually, whatever we studied so far, see this is the branch for not equal conditions. Okay. So that also done is a displacement type instruction they are supporting. After that, now loop statement also how we are realizing see the loop state when after when this come here then again it will go for the instruction set. So that's also possible in case of our MIFS code. So MIFS compile code would look like in this way. So I think in basic blocks is a sequence of instruction with no embedded branch and no branch. Basic blocks is a very important concept. In compiler you will find in compiler chapter, that means in fifth semester you will understand it very closely. There is a chapter, it's a directly directed acyclic graph. You will find the use of the basic block. Fundamental of the basic block is there. I can segment a code in such a way that no embedded branches are there. That means within that I don't call any other branch or come or jump. Some situation will not there. But our basic blocks are executed sequentially and no branch target access or beginning. That means something will be turned and something will go out. So within the basic block, there is no jump or such type of thing. Jumping is required. Then you have to consider another single basic block which will jump, but within the basic block it not happens. So basic block is a sequence of instruction, no induction like in this way. So once it start, it will compile, then it will finish. In between that, no jumping from other codes are allowed. Compiler identifies basic blocks for optimization. That means very important part in compiler optimization. Sometime loop, suppose this is a loop computation. There is a looping variables are there. And I found some variable in the loop. Suppose you have sometimes one examples I am giving you. I will come to this point again here. Suppose I have whiteboard. I am just using it. Suppose now I'm telling that, am I audible?
Yes.
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Now you're not audible, sir.
Sir, you're not audible.
Suppose you are writing sum equal to 0, sum equal to sum plus I, and here you are writing for I equal to 0 to I less than 10, I plus plus. Then you have written this code. Okay. And I found the computer part, it will be considered, it is a computer part, it will be considered as a my one single code. So I will consider this is my basic block. Actually, this is my basic block. Okay. So I can say because it's a sequential organization, I can say basic block. Okay. Now in the basic block, it means there is a input and the output is coming out. And inside there is no jumping. So inside this code happening. But if you notice it, the sum equal to 0 is once initialized is sufficient, or every time you have to initialize it. Dear student, can you specify this point?
Sir, for one
Every
time,
time.
sir.
And I am asking
I-
that every time it is very good every time to initialize, or only once it is a big good practice.
Only one.
Sir, only
I
one.
Sir, only once, sir.
only once, but
Only one.
what happened? It is doing every time.
It is
So it's
getting utilized
completing
to
every
Yes,
single time, sir. So
every
it's
time.
getting
But
using the
success.
now,
sum.
okay, but if you notice the code, actually the main interesting part is that if you write the code is correct or wrong. If you see in text of C context, is code is correct or wrong?
Correct, sir.
Code is correct. I think there is no problem in the code. But if you notice in architecture view, there is a register where suppose register I, where some value will be stored. So this is the register 1 I am telling, where the value of the I will be written. Another register, though it is constant value 10, suppose this is maybe n. So another register contain the value of n. So this is a register 2. There is register 2. Is it clear? Another point is that register is that sum. This contain the value of the sum. Okay. Am I correct or wrong? So what happened that in these cases, if you keep it outside, then what will happen? Initially 0, 0 plus according to the value of I10, the content will be updated. Okay. Am I correct or wrong?
Yes, sir.
Yes, sir.
The container, if I don't want any print statement, printf here percentage d, suppose sum. If I would like to print here, then this is okay. But if you would like to get on the final sum, that time will be error due to the presence of this.
Yes, sir. Because every time the for loop runs, it will initiate the sum to 0.
Yeah. Yeah.
So we will only get the value of n in the print statement.
Yeah. But suppose that I would like to print the value only after summation or the other. In this case, there will be no problem. Okay. I will get all the sum individually value will be printed. Okay. But my question is that our target that if this value is not is required only once applicable sufficient, so you keep it outside. Am I clear?
Yes.
Yes.
Yes, sir.
So this type of statement is called loop invariant computation. Is it clear? So our target that always outside, keep outside the loop, all this type of loop invariant computation, which is not associated the loop principle, but even it will increase the headache. Clear this part? Are you getting my point or not? Is
Yes,
this
sir.
part clear?
Yes,
Okay.
sir.
So loop invariant computation is a very important task, and sometimes it happens that you can't avoid it. So that's why the principle states that if you are doing some loop invariant computation, so always go for such things that which will give you the best beneficial in the design principle. So in the basic block design, the part whatever I mentioned in the basic block design, it is understood that in the basic block part, in basic block part, no embedded branches and no branch targets are there. A compiler identifies basic blocks for optimization. So optimization is possible when loop invariant computation keeps outside the basic block. The one step, like in this way, you can do, and since basic block encompasses only those instructions who are closely associated and there is no these two criteria is fulfilled. Advanced processor can accelerate execution of basic block. So because less number of jumps and all these things are there, so it will be good beneficial to all of us. Is it clear this part? So more conditional operations are using here. One by one, I have given here some branch target, sign, unsign, procedure calling, register uses, procedure user coordinate. So these are the all for MIPS instruction format, and I will give this slide for your reference and you study before you studying the MIPS operating system, MIPS simulator. Okay, got the point? So a lot of things are there. So we are not following this. In next time, you will follow this part. One very important part, I think many compiler produce object code directly, but nowadays the concept of the assembler is no more is required. From compiler to direct executable codes are possible. The linking is done and assembler done by automatically. So that is the one of the big issue. Earlier days, all these things, assembler is a two pass assembler, the first pass, second pass we have studied so far. So for time being, these concepts are no more required for you to study. But this is the follow how actually code is executed.
Sir, you will send these notes not on Moodle but through WhatsApp, sir.
Yeah,
Okay, sir.
but unofficially is a
Okay.
copyright document I have collected from IIT Kharagpur, one of my faculty professor there.
Okay.
So he has given me and he told that it is a pirated copyright issue because company can case so
Yes,
then
sir.
generate open. But for you study, you should study it. Okay,
Okay.
that's I have given all this thing. Apart from this, you study by yourself. Okay.
Yes, sir.
Now we will go the last topics of this today's discussion from the performance matrix. Then this chapter instruction set architecture will be almost finished. Our second chapter, then we'll go to the third chapter. Is the slide visible?
Yes, sir.
Okay. So in performance matrix, you will find that the whatever we are following the slide, particularly the performance oriented, that means how actually I know we have studied so far instruction set architecture, we have studied so far the related the difference issues actually with the MIPS simulator also. Now our question is come, when would you want to compare the performance? That means you would like to compare. Now you would like to compare the performances, then what you should do? Just 1 minute, the slide is not visible to me. Dear student, today I am keeping the classes up to this because some important meeting call has come. I forgot that after 3 the class is there. So tomorrow, from Monday, I will start this chapter. Okay?
Okay, sir.
Okay.
Thank you,
Okay,
Okay,
sir.
okay.
sir.
Thank you.
Thank you, sir.
Thank you, sir. Thank you.